Good afternoon, everyone. Very excited to be here to be talking about the post-training verifiable agents. So the Agentic AI course is a super exciting course. I believe that you'll be able to learn a lot from lots of people. First of all, the disclaimer that everything I talk about here in the lecture, all the views I express are solely those of the guest. It's me. I'm not representative of the company, including NVIDIA or UC Berkeley. So we'll be focusing on post-training verifiable agents, which is a very important topic in building highly reliable agent systems. From the basic requirements of building agentic models. So how do the agentic models differ from traditional large language models? From the very early days, when LLMs was first produced, we use a technique called reinforcement learning from human feedback. At that time, the language models really trained to align really well with human preference. For example, they interact with you, they really understand what you're saying, make you feel better. But later, essentially all the frontier labs and all the model vendors started to add these agentic capabilities to their models. And precisely for agentic model, the model is really aligned with environment feedbacks. By environment, I actually mean something very specific. Later, I will detail. They are designed to provide interactions to maximize verifiable rewards, in addition to human preference. So basically, when you're actually talking to those agentic language models, they are supposed to really understand your intentions very well, because it's designed to first maximize human preference, but also at the same time, it's designed to help you accomplish tasks. That's extremely critical. And for evaluating the quality of task completion, we usually use something different from generic reward models. Because for certain tasks, maybe there will be a few correct answers, and there will be really wrong answers. You absolutely cannot do that. And usually for human preference, the situation is slightly different. So brief recap of earlier models that were trained to be great chatbots. The way we trained usually is the following. Say, you collect lots of human assistant chats. Human says something, assistant says something. Then later, you would like to rank the assistant responses based on human preference. Maybe you do crowdsourcing, ask lots of people. Then you collect this human preference. Then you try to figure out reward modeling technique to come up with a reward model, basically based on the human assistant interactions, trying to grade whether a certain response from the assistant is good or not. Once you get a really high quality reward model, we like to start training the language model so that it can actually behave better in terms of maximizing human preference. There are many algorithms you can use here. So here I also include the SFT. Sometimes people say SFT, which is the abbreviation for supervised fine-tuning, is mostly used for strictly mimicking the expert behavior. I include here because SFT actually is also being used a lot, even when you are given the reward model. So the intuition is that I can use a reward model to grade multiple different responses from the assistant. Then basically, I can only choose those assistant responses that rank very high by the reward model, then conduct supervised fine-tuning on those responses. I can also use other reinforcement learning algorithms like PPO and GRPO, any algorithm you come up with or you have heard of, finally to produce a model to maximize human preference. Hopefully by talking to that model, you feel that it's really engaging, model really understands you, you feel very happy about this. Feel free to also stop me when you have questions. What more is necessary? So it turns out one of the key applications of LLMs is actually agentic tasks. Conversations is not verifiable. There are also usually no clear single correct answer. You use a really sophisticated reward model to model preference and requires interaction with the user only. But in terms of enterprise applications of LLMs, many tasks they have they actually require the deep interaction between the human, sometimes multiple people, multiple assistants, and many other entities, including the environment, specific code repo, specific software system, and many different tools. So basically, you need to make sure that LLM is able to understand the feedback given by many different entities, understand the full states of this environment, and also make sure that when LLM performs a certain task, it's able to really produce the correct answer. And there's a very clear verifier demonstrating whether the answer is correct or not. And you should really not produce the wrong answers because that's going to make the whole system totally crash. So sometimes people say that you can use other deterministic system to help fix that. But one thing people have found is that if the LLM is not strong enough in producing essentially right answers, it's very, very hard to build a reliable system, even after you do lots of software engineering on top of this. So precisely for today's models, they are trained to be great agents. The user no longer asks a question saying, how are you? You start very engaging conversations. Your user has a very clear target. Sometimes even vague, but there's something user wants to accomplish. They say, I want to achieve this. I want to book flights. I want to talk to my server system. Then the LLM needs to be able to understand this and precisely execute. So there are many different ways to evaluate the outputs of the LLM and the system. There are different rubrics defined by people. You can also write down different ground truths. You have a very clear recording of the environmental states. And you also conduct lots of unit tests to check the outputs of the LLMs. By doing this, you get very good signals. You understand whether the output of LLM, in this case, is right or not. And then you start to use lots of other post-training algorithms. Again, super fine-tuning, PPO, GRPO, to actually improve the model. So eventually, the goal is that you want to construct a very strong agentic model to maximize correctness by interacting within sandboxes with very complex tools. I will try to make everything very precise later when we go into the details of this. Okay. But what is needed to train the verifiable agent models? In particular, it is a very important topic. Lots of people in the community are focusing on. I would say that there are 3 core steps, and each one is actually very challenging. These days, it really requires the collaboration of many people across industry, across academia, to contribute to this so that we'll be able to get very, very strong agentic language models in the future. So the first step, I say, to get good verifiable training data to train agents. Without high-quality training data, we simply cannot produce very high-quality agent LLMs. I'll be talking about the challenges behind getting very high-quality training data. The step 2 is actually evaluation. You collect the data, you figure out your training approach, you train the model, but then you need to really understand whether it's good or not. So generally, there's a very dangerous trend of really entering in this illusion that we feel we collect the data is comprehensive enough, then we only test the things that are really aligned with our data. It really appears that everything's working really well. Then suddenly we test everything in the wild, things start to break. So how do we define verifiable agents? We're actually talking about some concrete examples. Maybe later I'll try to make it even more concrete. For example, one thing could be that you're solving a math problem. Then the computer also has access to certain tools. For example, Python coding tool. Then after accessing to the coding tool, writing lots of codes, understanding the problem, finally the LLM is supposed to produce an answer. For example, the final answer to the math problem is number 2. Now I want to make sure it's precisely the right answer. So it's just one example. The other examples in software engineering, you're able to produce a code script. And then there are many different ways to check the validity of the code. For example, there are so many different unit tests I can write. You need to be able to pass all of these tests to make sure that finally it's correct. Turns out it is really complicated question. So there are so many different verifiers you can build. And the current challenge everybody is facing in the community is that we haven't got enough strong verifiers to really make sure that we capture all the corner cases of the intelligence. So the third step is actually also about training. So this is also a very complex topic. Until today, many people, community are trying very hard to research on this, which is that I got very good training data. I also figured out how to evaluate my agents. But what exactly is the best way of feeding the data to the model so that the model's intelligence, in fact, actually improves? In some sense, when we think about building the verifiable agents, we really think about this essentially as training a human being. So when you're training like engineer in a company, what usually you do is that you first give some instructions. You say, well, maybe you're supposed to write code in this way, or you're supposed to operate the software system in a certain way. Then the person started doing that, started writing code, started interacting with the software system, submitting tickets, things like that. Then sometimes they will make mistakes, but they will receive some feedback. The key challenge is that for a human, you can just tell the human, well, here's the feedback I give to you. What about next time you do better? But for the machine, the hardest part is to transform this natural human interaction into something that's implementable by an algorithm. So the algorithm needs to make sure once the LLM first attempts something, but it made a mistake, I give the LLM very detailed feedback. How do I guarantee the next time the LLM also attempts the same question, the quality of its attempt actually improves? If I'm not able to achieve this, then basically I'm not able to replicate this natural feedback loop of human learning, then we're going to really hit a plateau of the final intelligence of the system. So that's why the step 3 is also extremely critical. We'll also be spending lots of time talking about step 3, including some approaches people have taken in the past. But I really want to emphasize that all the 3 steps, they require very extensive research at this point. So it's actually a fascinating opportunity for everyone to get into the field at this point. Okay, talking about the first thing, getting good training data. So agentic models maximize verifiable rewards. What exactly would be the core components of training data that we specify to really make sure that they're actually of high quality? So I want first of all to emphasize 3 different things. They are kind of very, very related. In certain literature, maybe they are combined together, but I do think that things are slightly different. So I want to emphasize 3 different aspects of the data sets. The first is called the environment. So how do I think about the environment for the agent? So say you build a coding agent, right? So basically, the agent takes in your instructions, trying to generate code in well-formulated the code repo. Maybe the code repo has some issues, there are certain bugs, you're supposed to fix that. The environment basically encodes the whole state of this repo. For example, the prefix and suffix of the code script, and lots of files we have loaded, lots of downstream tasks we need to deal with. They describe the states of the environment, and also it includes lots of system prompts people have already set up for different parts to work together. The second part I want to talk about is tools. So basically, the agentic LLMs, they are trained to generate tokens that are consumed by software tools to provide additional relative information to the model. So precisely, you should think of this as additional, in software engineering language, additional APIs provided to the system. For example, you call the system, well, if the user asks you a question, what's today's weather? LLM is not supposed to know that, but LLM really knows that it has access to certain APIs that's able to access to this weather. The LLM is supposed to be producing the exact API call to the external system. Then external system should be able to feedback the concrete information regarding to this weather. The LLM should be able to internalize that, and then finally present the final answer to the user. So the APIs could provide additional information. The APIs could actually also help change the environment state. So basically, you're working in environments, the state is really complex, has lots of different moving parts. Then maybe you are given certain tools to help you modify the states. Because maybe in order to actually accomplish certain tasks, there will be certain states that needs to be changed. Maybe even the user doesn't know that. But as a very strong agentic LLM, the system is supposed to know that. User gives a task, then the agent is supposed to be able to decompose the task, figure out what exactly are the right tools to call, change the environment states if necessary, and finally produce the answer. And the point 3 is really about checking the answer. So basically, model are trained to generate tokens. It produced the answer, but how do I even know if the answer is correct or not? We need to build the so-called verifiers. The verifiers will tell you whether you have really succeeded in completing the tasks. In some sense, it's also quite challenging because there are lots of intricate issues related to evaluation. Maybe you really produced a right answer, but it took you like so many steps. It consumed so many tokens maybe I'm actually also supposed to penalize you due to this. So even for that, turns out it's really very good to think about verifiers not as a single number, checking it is correct or not. Think of this really as a vector, talking about evaluating the quality of the model from many different perspectives. It can be unit tests for code, we just talk about, math checker for proofs, or for web tasks. You can also check whether you have really accomplished certain tasks on your browser. So that's the three aspects. Then I want to talk about some of the challenges in preparing the data. So the first step is to get good training data in training this very strong agentic LLMs. And in order to really make sure it works in the wild, it appears that you need to really follow a principle to say, I need to understand many different environments. I need to have a system that's able to use many different kinds of tools. I also need to make sure the system does well under so many different verifiers. That actually is very interesting, and it's also the lessons learned by the whole community over the past 2 years, showing that one definitely shouldn't be tricked to believe that the whole system is working very well when you're actually only working with very few environments, very limited verification, because the system would indeed break once you go beyond the scope of your data. And the key challenge here is really make sure that you got enough coverage. So here I want to give you some more examples, talking about what we have been discussing on high level. Say you want to train a very strong agentic system, and then there are so many possible combinations of environments, tools, and verifiers. For example, in environments, there can be math. For math environments, you are given a problem, then interact with the user, the IAM provides the answer. Then you could have a math verifiers, proof checker. Then in the environments, you actually could also have access to different coding tools. That's why these days, sometimes when you use ChatGPT, you see that you ask a math question, ChatGPT actually would call Python, try to write some script to really verify that the answer is actually correct. Or you're working with enterprise software, for example, here talk about the sales assistant. Then it could to access different software API tools. Maybe a salesperson wants to ask today's weather, I want to get news. Maybe I also want to access a database built in my system. Maybe I want to understand who actually are my customers, what exactly is the progress with customers. And maybe I want to really write really precise query language to query the database, and also to make sure that I'm able to internalize the outputs from the database. So many different types of environments, tools, and verifiers is very important. We achieve very good coverage, and it's always an interesting challenge to make sure that we have indeed covered all the important aspects we care about. So that's why it's also super exciting time to do research, because always we get something more to work on. One thing I want to really emphasize, which is verifier quality. And these days, when we look at the open source community, it's actually one thing that's really lacking at this point. So generally, one thing one has observed is that it's very easy to think about one rule to verify a certain answer and just to put it down as a single verifier. But the thesis that has appeared again and again in the community was that whenever we thought we have built a very high quality verifier in checking the answer of the LLMs, turns out we have missed some corner cases. So here I'm just showing you something very basic, which has already been covered by the community, but there are way more complex examples showing that it's actually quite difficult. Right. For example, let's say the user has a question. I want to ask how much change will I get back if I buy a drink for 50 cents and give $1. The IAM could give multiple different answers, right? So basically can give 1/2, 2 over 4. Then in terms of the verifier quality, you are really supposed to say that all of these are correct, because they actually indeed tell you what's the right amount of change. However, user's question could actually also include something more stringent. For example, in addition to just asking you how much change would I get back, I have an additional request please just give me the simplest form. So once I have that, the verifier answer is supposed to be different because supposed to be 1/2. Then in these cases, in particular, it's very easy to make mistakes when you are constructing the verifiers. And those cases are usually very costly because generally these days, LLMs are already quite strong. You'll give LLM a very simple question, it will be able to answer it. And only in those challenging cases would they sometimes make a mistake. But if your verifier is also wrong, didn't capture the nuance in the question, you absolutely cannot further improve the quality of the LLM. So that's actually one thing we really want to emphasize. The question is false positive or false negative, which one is better or worse, maybe more significant. Actually, in our experiences, I would say that it's very important to minimize both types of errors. Because it's sometimes, of course, it's also because in different applications, you assign different weights to different types of errors. But in reality, you can always find the interesting applications where a particular type of error, either false positive or false negative, could produce catastrophic results. So you really want to make sure that doesn't really happen. You want to conduct minimal software engineering to finally fix the outputs of the LLMs. So I'm just showing this as an example, trying to convince you it's actually quite challenging to write very good verifiers because there are lots of nuance in evaluating the final output. Okay, so then we talk about the first part, which is how to get very high quality training data in order to train very good agentic LLMs. Now we're talking about the second component, which is getting good evaluation data. So it's kind of connected to training data, but in reality, when we focus on this, we do try to view this from different perspectives. In some sense, even trying to tackle certain aspects that are not really being paid attention to in training, because the intuition is that we really want the training to be generalizable. So basically, in collecting training data, there's actually no way we have collected all the data in the world. For example, just to think about the amount of data human beings would produce when we are interacting with the internet, when we are interacting with a browser, or when we are doing math proofs, or when engineers code, that's basically unlimited. There actually is no way we just cover all of them. So the whole point is that you want to build a very good pipeline to make sure that once you achieve solid coverage of training data, it's supposed to generalize to many environments you haven't really seen, because there's actually no way you see all of these different environments. That's actually one task that this good evaluation is supposed to capture. For example, here I'm just listing very few like targets of a good agentic model. Later, I'll be talking about some existing evaluation systems people have already built to capture those targets. For example, one thing, I want agents to work with many different tools. It's so natural. If the agent can only work with a few different tools, I give a new one, maybe the user modifies the tool, then the system just breaks. We really cannot tolerate that. It's also expected to work for many different use cases. It's also very natural because maybe the user today also comes up with a different use case. You also do not want the system to break. It operates with software system 1, but there's software system 2 with slightly modified API. You want this to also continue to work. And you also, another core aspect in particular in the human interactions, I think it's also being surfaced again and again, is that agents are expected to work under vaguely specified instructions. So in the very early days of agentic systems, when people are designing evaluation, it's always like the user would have a very clear target. The user would say, please conduct this. Then you see the LLM behaves very intelligently, is really able to decompose the problem, execute the task, calling the APIs in the right way. But later, in reality, people really found in the wild, when people started to interact with those agents, they have absolutely no idea what they want to do. So basically, asking random questions, they are actually hoping the agent could tell them what they should do in order to accomplish this task. So in some sense, it really means that you need a very smart system. The system should be able to understand human intentions, by proactively talking to people, but also at the same time produce very precisely formatted outputs so that they can actually interact with very rigidly formatted software systems. So number 4, agents are expected to work under many different software systems. For example, you use Cursor in programming. I build a system for Cursor, works very well. Suddenly, you change to another system. I use the exact same LLM, completely breaks. It's definitely not ideal. And if that really happens, that also brings people to question the quality and the intelligence of your large language model, because maybe the LLM just simply isn't smart enough to understand those changes. This generally will be very problematic. The 5th one is very generic. I call here expected to be robust. It's really because there are so many things could actually go wrong in interaction with humans and with software systems. Human beings may not really know what they want, and the software system could also sometimes produce issues. You want to make sure that the LLM really behaves as a really smart person, just like very high quality engineers to be able to debug all different issues that emerge in our daily life. So the slides will also be made available online. Here, I just want to give you some more concrete examples of what people have already done in the past. So those benchmarks, they do map to the specific requirements we have been talking about here. For example, 1, 2 is about different tools and different use cases. So on the left, I'm showing the off-the-shelf benchmarks, which actually cover many different use cases, many different tools. And there's also number 4 on the different software systems. So here I'm talking about different agent harnesses, which I will also describe in detail. And number 3, 5 here is focusing on unit test evaluations, checking robustness of the outputs. Okay, so maybe I'll start from the left. So in the past a couple of years, the community has developed some really significant benchmarks, trying to push the intelligence LLMs higher and higher. The benchmarks getting harder and harder. Generally, people have achieved tremendous progress. And indeed, per our observations, certain tasks that in the past were believed to be very hard for LLMs, these days they can actually solve them. Turns out they really produce a very significant productivity gain. Here I'm talking about a couple of them. For example, a sweet bench really is really challenging the LLMs to really solve this very, very sophisticated GitHub issues. Many times it really needs to involve so many different tools to solve these issues. And also through solving sweet bench, also made people understand that you're actually supposed to be interacting with different harnesses. I want to really emphasize this because there's a very complex like GitHub issue you need to solve. But to solve it, many people actually operating in different environments. For example, in one environment, maybe you have a function called open this file. You are supposed to just call this function to open the file. Maybe in another environment, you do not have this function. You have some other command line tools you call to actually accomplish the same task. So the whole point is that in order to check your capability in solving sweet bench, you're actually not supposed to be only sticking to a particular harness. You're supposed to be trying so many different ones, showing that for this particular task, maybe when I give you this set of different tools, another set of different tools, slightly different formulated tools, are you able to solve it in all circumstances? If you can, it really means that your intelligence has already achieved a certain threshold. That's actually an extremely important point. There also are different other benchmarks like Tau bench, BFCL, also from Berkeley, complex function bench, covering a very wide variety of different tools, different application scenarios, just to make sure that you do not overfit to a particular application. And there are also different unit test evaluations. For example, those actually could be would be the focus of many community members from a long time ago, saying that I want to check the structured output adherence, which means that maybe in many cases, I want you to produce a JSON output. I really want to make sure it's really exactly right JSON. So I want to make sure you do not really need to later write a very complex software engineering code to correct the mistakes produced by LLMs. There has been lots of attempts in the past to produce such software engineering tools somehow to reduce the burden on LLMs. But later, essentially, what everybody observed is that if the LLM itself is not intelligent enough, is not able to produce very high quality JSON or structured outputs, it becomes essentially impossible for anyone to fix the issues later. Because lots of issues, they really involve very nuanced understanding of the system. It really requires a system with very high level intelligence. So basically, you cannot easily fix it using very simple rules. So one point to summarize what we talk about, which is a holistic environments. We want to make sure we check all kinds of capabilities, LLMs, humanities last exam, general scientific knowledge, AME in math, sweet bench in coding. It's supposed to be combined with different harnesses. And I want to make sure that we really create a super strong, super intelligent model that's able to solve all of these tasks under all kinds of combinations of evaluations to convince ourselves that indeed we have made progress in terms of enhancements of intelligence. So keeping the definition of intelligence holistic is extremely important because these days we are trying to utilize the systems to increase our productivity. And one thing has come up again and again is that the system we are dealing with in practice, as a scientist, as an engineer, as a researcher, it's just so complicated. So in order to make sure the system LLMs can actually help us, we want to make sure it is smart enough. Okay, so to continue what we talk about, good evaluations need to account for all of these things, evaluate on many different tasks and verifiers, many different ways of letting the agent explore in a benchmark sandbox by seeing how the accuracy changes as you swap out the harnesses. You make sure that if you see sometimes a very significant performance drop, maybe means that you did something wrong in training. Then you need to figure out new ways of training to fix this. You also need to deal with many different tools, how to use different tools in different action spaces. Ideally, you really stick to the same model so that the model needs to itself figure out what to do. So in summary, evaluation is extremely important. Lots of people here are also working on very significant topics in evaluation. It is definitely something we need the help from the whole community on, because only by collectively working on this can we really understand the limitations of existing agentic system and make progress. So it really needs to be holistic and good measure. One last thing I want to talk about before we go into the training aspect is actually also about maybe approaches to combine different tasks and harnesses to evaluate. So basically, say you have already come up with lots of different evaluations, right? For example, checking the quality of math, quality of code, swapping the harnesses, making sure things are actually good. Well, then you saw some good numbers. So are you still really sure that you didn't really overfit all these benchmarks? Because maybe in this process of iterating on your post-training, you have collected some data which is really similar to some of the data in your evaluation, or in the whole community, maybe certain models have already been contaminated. Maybe certain evaluations should no longer really work. Are you really sure it's not happening? When you see a high number on certain benchmarks, say on sweet bench, are you really sure your IM is actually very strong? I would like to emphasize that there's also a very important community effort to continuously trying to check the quality of evaluations, which is also an important aspect of IM research. So basically, several aspects one could consider. One thing is about hardness. So basically, suppose at the very early days, maybe IMs are not intelligent enough. There will be certain benchmarks. Maybe all the IMs would score very low on these benchmarks. But maybe these days, for example, like GSM-8K, everyone scores very high on this benchmark. Now you say, well, I achieved a 5-point improvement on this benchmark. It's really unclear you have actually made some progress, because there's also maybe likely for the specific base model you work on, the model has already been exposed to certain data that's very similar to a GSM-8K evaluation. You really do not know what's going on. You need to continuously monitor hardness. You also need to continuously monitor separability. By that, I mean that when you ask a question, And you ask many different LLMs the same question. Ideally, you are supposed to see that LLMs that's supposed to be stronger, they answer the question better. The LLMs that's supposed to be weaker, they do not answer as well. In that case, we would like to say that the benchmark is able to separate the capabilities of LLMs. Because if that doesn't really happen, or you observe that while the weak LLMs and strong LLMs, they produce very similar scores, maybe the reaction should be that you abandon this benchmark. Because there must be something that has gone wrong in the past, either in training or in some other types of evaluation that maybe has hurt the credibility of this particular benchmark. There's also, of course, issue of diversity, which is also the topic we have been talking about again and again, which is that you need to have very good coverage. So if you do not have very good coverage, you produce high number, maybe on data sets, you only have like 50 different prompts. They're all very similar to each other. You produce a high score. Doesn't really mean that your system actually is behaving very well. So all these are very important topics. And it's really a very significant community effort to make sure that we do not fall into the pitfalls. There are so many benchmarks are really public, so all the data is available. There are attempts people have to create the private benchmarks to really track the progress. Clearly, there are. So actually, lots of individuals, community members at companies, they would like to create a private benchmarks to really check that. So in some sense, maybe the situation everyone wants to see would be that we need to see way more benchmarks being proposed. Because private benchmark is good, but if you have a very static benchmark, then people try to fit it so many times, maybe it still will lose credibility. And ideally, let's say for public benchmarks, if the community can continue to produce more and more benchmarks in all kinds of different environments, then it's actually very hard for everyone to overfit to all of them. Then there was a saying that, well, suppose you have only 5 benchmarks in the world. You have a benchmax them. So basically, you claim your model is really the best on the 5. Maybe it may not really work on all other benchmarks. But if the community has collectively produced 1 billion benchmarks, right, covering essentially everything we do in reality, math, coding, computer use, whatever, then say that someone comes up and say that I have an overfit to all 1 billion benchmarks. Then maybe you have already achieved AGI because they really have already covered everything that you care about. So in some sense, benchmarking efforts is really a very strong community effort. So we really would only be able to succeed when more and more people are producing very high quality benchmarks covering their use cases. So that's actually also an aspect I personally feel that academia can really make a very strong contribution to because there are many people working on so many different topics. So trying to really capture what is actually missing in the existing training of the agentic systems. Great, then we'll be talking about the third part, training while. What does the training agent mean? So training is a very complex topic. These days, we still have new algorithms coming up every day. But generally, I want to talk about the principle of training. So in terms of training, you want the agent LLMs to attempt different actions in your specific environment and see what gets it to the final answer the best. Whichever gets you the best results, you want the model to reinforce and repeat. So here I'm talking about this paradigm. See that on the left, there's an agentic LLM, which is supposed to be smart. Okay, you are training the agentic LLMs. So you give the agentic LLM a certain task. You say, well, please complete certain task, try to do it. Then LLM would make lots of attempts. Here I'm showing 1 to 5. Go to the environments, maybe in each attempt, it tries to call different tools, try to retrieve different information, try to make a final decision. Now finally, there's a verifier saying, oh, for each attempt, is it correct or not correct? How much cost has it incurred? Then ideally, even without demonstrating how it trains this, we already know the target. The target will be that I want to make sure at the very end, after training, the IM is able to generate the correct trajectory, so the attempt is successful. Maybe ideally also with the minimal cost. And there could also be other aspects I care about in final evaluation. So what are some aspects, some core characteristics you focus on in the whole training process? I'm talking about two here. There could be many others. One thing I want to emphasize that you want each attempt to be very different from each other. Since you want the model to reinforce or discourage many different styles of attempts, it's just like a human being, right? Suppose I want to teach a kid to do something. Then ideally, if the person is able to come up with multiple different approaches, they're very different from each other, then ideally some of them is correct, some of them is incorrect. After I give very detailed feedback, I hope the person can learn very fast. But the issue is that if the person is only able to come up with a single answer and it's wrong, then by telling the person it is wrong, it did give some information, then it really appeared that it's slightly harder for the training algorithm to work. Appears that you didn't provide enough amount of information, at least for many algorithms, to be able to improve the quality of agentic systems. And a second aspect I also want to emphasize is that every attempt would cost compute to sample and process. You ask LM as a person to say, oh, what about you try this? They tried it, and it's totally wrong. You ask to try 100 times, all of them are totally wrong. That wouldn't be very satisfactory, because each attempt costs lots of money, lots of resources. You do not want very silly attempts. So somehow we are really in a delicate situation. So if we give LM a question, it's super easy, all the attempts are all exactly correct, it didn't learn anything. But ask LM to attempt many times with all failures, cost lots of money and resources, and you also need to spend lots of time figuring out how to make the LMs learn. So it's a really complicated process. Till today, I believe the whole community is still trying to figure out what's the right way to deal with this. But I think that by connecting this better with the human learning process, it did raise lots of really fascinating questions about that. So we want to talk about some of the existing approaches taken by the community. And I really want to emphasize that the existing approaches may not really represent the best approaches one can take. So lots of research to be done in general. Also, from a certain point of view, if we really go back to machine learning theory, certain approaches being proposed here are also not exactly right. So one big issue we are dealing with in training LLMs is that the theoretical foundation usually cannot connect very well with existing practices. So it's really, I believe, the task of whole community to come together to figure out how we can propose better formulations. But to connect what I talked about before, there generally will be two stages in training the agentic systems. The first stage we call supervised fine-tuning, or SFT. So it is basically imitation learning. I would like to imitate demonstration trajectories that achieve correctness. What that really means is that suppose at the very beginning, the IM doesn't know anything. You give the IM a task, it will output some garbage. That's exactly what the situation we talk about of the silly attempts. That cost lots of money and resources, we didn't make any progress. In that case, usually to jumpstart the whole system, what you would do is that you would like to connect some demonstration trajectories. You say, well, here's a particular query. I would like to show you, as a human being, the right set of actions you need to take. Maybe access this database, also access another API, talk to another system, finally this whole trajectory. I just show you that. What about you try to replicate this? Next time I ask you exactly the same question, what about you try to produce exactly the same answer as the demonstration I've just shown to you? So the hope is that I want to minimize any silly or non-meaningful attempts. The second stage is that, well, maybe you are already entered the stage where I give you a question, sometimes still make mistakes, but they're not totally wrong. Actually, sometimes you are reasonably correct. In this case, I would like to let you explore. Because the more you explore by yourself, the better you learn. In some sense, very similar to the philosophy of human learning. Say, in school, if the professor only gives us the precise answer to the question, so you just copy this. We're not allowed to produce any homework to be graded by the professor, and we don't get any feedback. then maybe different people will make mistakes in different ways, right? I have this particular type of mistake. I want to know it was wrong. Nobody give me that because the professor only give me the exact right answer. There's new question coming up. I have no idea. That's I actually tend to make certain type of mistakes. So the real way to learn is to let the model explore and reinforce trajectories to achieve correctness and discourage the ones that do not. Going back to the previous point, you actually also want the model to produce very diverse trajectories so that if you go wrong, I want to see you go wrong. Then I tell you it goes wrong. Instead of you say, well, essentially everything is correct, but they are always the same. Then you didn't really learn too much about this. You want to reinforce diverse great attempts from the current model and discourage diverse and bad attempts. Both sides need to be diverse because diversity really accelerates the learning process. So to really talk about the details, SFT stage and RL stage, I personally feel it's very intuitive because it maps really well to human being learning. SFT stage is basically maximize the likelihood of sampling the demonstration trajectories and minimize likelihood of sampling anything else. Give you the particular trajectory, say, well, what about you sample this? Hopefully it really works very well. It's just here so that we can sample meaningful trajectories. So one key aspect of SFT is that demonstration samples needs to be diverse. So basically, if you give me very few SFT samples, very similar style, then maybe what has happened is that the model is not able to generate diverse attempts later in RL stage, which is bad. And similarly for the second requirements, here I wrote a requirement which is SFT should be light. The intuition is also exactly the same because if you have conducted very heavy SFT, which means that you have basically tried to teach the model for every question I collect in training sets, I tell you what is the right answer. And I tell you, please remember this, it is exactly only right answer. Then later the model will lose the ability to figure answers by its own. And in reality, the real issue is that no matter how big the collection of your training data is, it can never cover every aspect of our interaction with LLMs and with humans. So if you really only teach the LLM to exactly follow your demonstration answers, generally it will really fail for tasks that are actually auto distribution. So in the RL stage, so here I'm talking about the technical details. You can find the details in essentially every paper in RL. In the rollout stage, I want to sample very meaningful but very different actions for the tasks, the environment and tools. You have limited compute. You want to make sure you get as diverse answers as possible, as meaningful as possible. Then you figure out how correct each action sequence is, how rare and useful certain actions are. Then you try to figure out how to update your LLM so that the next time when you try to generate answers, you generate more the correct answers, you generate less the incorrect answers. That appears to be the hardest part. So in some sense, it's also similar to what we observe in human learning, which is that when the professor gives the students a task, then everyone submits the homework. The hardest thing is really to make sure that the next time when there's a new task coming up, everyone is asked to submit homework again. How to make sure that you really have produced a better answer. So generally, for human beings, people actually differ in this way. So many people, by giving the same feedback, actually they produce many different answers once given a new set of tasks. That's exactly the same situation for RL algorithms. You use different RL algorithms, give you the same amount of data, then later turns out the quality of the system actually is different. Summarize, SFT just here to discourage meaningless and low quality rollouts attempts, and RL is here to truly reinforce intelligence. So I indeed have prepared some more slides talking about the details of RL because I do believe that it's a very critical research topic. The question that has been a certain work, actually also work coming from NVIDIA, talking about maybe in certain cases, one can remove the SFT stage. We conduct more RL. By the way, it's also a trend demonstrated by many frontier labs. Consume more compute. That actually also goes back to one of the core things I talk about when we are talking about training algorithms, is that these days it's really unclear what is actually the correct training algorithm. So because in some sense, for those of you who are very familiar with machine learning theory, you know that the current algorithm formulation, for example, combination, SIT, and RL, they actually do not align very well with machine learning theory. If you started from a theoretical perspective, working on simplified models, you wouldn't be doing this. You'd be doing something else. And on simplified models, something else will work so much better than these approaches we currently take on LLMs. So that's a very big issue. So that's why we believe that more exploration in terms of different architecture, different algorithms, better ways of utilizing data, both pre-training and post-training data, is very critical in the community. Because currently, it would be very nice if we can move closer to the theoretical principles while doing something that's implementable in practice. This is actually currently a really important research topic. I personally would encourage everyone to really dive very deep into this because I believe we definitely have not converged in terms of what's the right algorithm to use. As you'll see, when I talk about later certain issues related to the algorithms, I by no means mean that those are maybe the really right approaches we follow, that they will continue to be right even 10 years from now. But maybe my purpose is really to show you certain observations people have made in the past in running certain algorithms. Hopefully, it can motivate you to design new algorithms that actually work better. Maybe one perspective is LLM could be considered as like pattern matching. Then you want to train the system to be able to conduct critical thinking and also be able to invent something new. First of all, my feeling is that it's generally very difficult to understand what exactly LLM is doing. Because when you really think about how do human beings learn, in many cases, suppose when we're actually trying to solve exam questions, right? We are attending a class, we are also doing pattern matching. Right, when we're in school, professor shows us one problem, then there's answer, then here's the next problem, very similar. We are also doing very similar things. So me personally, I feel that it will be fascinating to combine everything related to human learning with LLM learning, which is exactly what we are trying to show here. So we have got some good intuition with human learning. We figured out how humans can learn better. But the issue is that many humans have no idea how they actually learned. Right, they did something, they got some feedback. Next time they did something else. But here we need to write an algorithm. That's actually the hardest thing. We have no idea how to write an algorithm. And in terms of human learning, there are so many things we want to learn. And there are so many ways to evaluate a person. Right, just like these days, students take exams from all courses. Right, are we really sure all the exams are really fair? They evaluate a person, the students in the right way. It's super interesting. So one point I'm trying to make here is that it's a so fascinating area to think about that we are actually absolutely at the infancy of the area. We really haven't figured out what's the right way to train those systems and also deploy them in certain other critical applications. But we have made interesting observations, which is what I'm trying to show here. Hopefully, the observations are insightful and can stimulate some of the research the people do, people in this course can actually do in the future. Okay, so then let's dive slightly deeper into reinforcement learning. I want to talk about 3 core aspects. I believe that we still need to do a lot more research around those aspects, potentially new aspects, but the community has made interesting observations. I want to share the observations here. One idea is to train for longer. So one intuition you situation you don't want to hit is that you got some data sets, you get LLM to attempt to solve the problems. You attempt once or twice, then later you found that it can no longer attempt. So every time it makes attempt, produces exactly the same answers, saturates. Okay, not able to train longer. Not ideal, because for human beings, we really get constant feedback. We are given a task, we propose a solution, we get that feedback. Next time we propose a better solution. Ideally, later we come up with really amazing maybe answers, maybe inventing something really new, conducting cutting-edge research, inventing general theory of relativity, right? It's there's a very, very high bar here, but it will not be very good. You say that it plateaus like very, very quickly. The second aspect observation people have made is that somehow you need to train on more difficult prompt and tasks. So intuitively also makes sense. So as for a human, suppose you are given a task to learn. You're only given really simple tasks. You already know how to solve it really, really well. You didn't really learn anything new. That's for LLMs, it's also exactly the same. But so we did talk about some of the intricacy related to this, because if the LLM is only given really difficult tasks, like solving Riemann hypothesis, nobody can really solve, and nobody can make any progress. So that's actually also a very big challenge. Turns out it's important to convert the intuition we have in human learning to LLM learning, which is also very big ongoing research project. I've been talking about some observations people have made. The third aspect I want to emphasize is to train on more diverse responses with high quality reward feedback. So which is very natural. As for a human, if you only interact with very limited subjects, for example, you only study a single subject, only take one course, and then you certainly would not be able to answer the questions in the exams of other courses. You need to do that. So you need to see many different meaningful answers per prompt as many answers as possible. So the good R algorithm should rely on those pillars, and they actually are even more pillars in practice. So I will very briefly talk about those pillars. One pillar we talk about is train longer, being able to train longer. So there has been many observations in the community talking about this entropy mechanism or entropy collapse mechanism. And actually many different papers have also very many other correlated metrics capturing something similar. But the idea is the following. So on the left, I'm showing you a plot. X-axis is the number of training steps. Basically, you train longer and longer. Y-axis is showing performance gain. So basically, how much the LM has actually improved. So yeah, I'm also showing this y-axis. I have two curves. One is showing performance gain. The other is showing entropy lapse. By entropy, actually means that when the LM is trying to generate its next token, as being specified in literature, it's a probabilistic inference because next token is sampled from a distribution, right? So by entropy, I mean that I basically compute the entropy of the token generation probability. By large entropy, it means that there will be high uncertainty in sampling the next token. Then if we have a high entropy, then very likely, if you sample the trajectory twice, you'll be able to get two very, very different trajectories. If the entropy is very low, think of the situation that whenever you are given a prompt, then you ask the model to predict the next token, then the model is always super sure next particular token is certain token with 99% probability. Then even if you run this LM, you sample it so many different times, you wouldn't be able to sample many different trajectories because only a single trajectory has very, very high probability. So what this plot has shown that if you do not intervene, if you follow many different algorithms, what's going to happen is that as the number of steps increases, the performance would gain. Indeed, you see in terms of reward, the model started to produce very high quality answers. Entropy started to decrease. So basically, later only learns that I'm able to only produce one answer. So then we ask a question, is it really possible that we still produce really high quality answers, but at the same time, do not achieve this entropy collapse? So later, answers all correct, still diverse, being able to explore, but ideally, for every question, I'm able to come up with 5 different correct answers. That's so fascinating because even for a human, it's actually very hard for a very hard task come up with 5 different correct answers. So there has been some observations in literature. Here I talk about 2 approaches people have taken in the literature to alleviate this issue. On the left, I'm talking about this on-policy versus off-policy issue. Okay, so basically, I increased the number of training steps. Then I observed that in terms of training rewards, which is the leftmost figure, I observed that for either on-policy or off-policy algorithms, the rewards actually increase in a similar manner, which means that I do get better and better policies. But precisely by on-policy, I want to emphasize that it really exactly refers to the setting that whenever I ask the reward model or a verifier to judge the quality of the attempts, I only judge attempts produced by the IM itself. So it is called on-policy, which means that I do not try to give you rewards or feedback based on the answers produced by other LLMs or produced by different weights. I really want to give you feedback produced by you at this point so that you can really learn the best. So on-policy really means that I want you to learn from your current mistakes, not the answers produced by other people. Intuitively, from the perspective of human learning, if the answer is produced by the students, then the professor, give the students very detailed feedback. The student can really learn the most. But if the student didn't write down the answer themselves, copied it from somewhere else, you give feedback, maybe the student can still try to learn, but may not learn as well. So that's actually intuition we are trying to borrow here, showing that if you use on-policy, the KL divergence between the policy you train to the original initial policy is small, and also the entropy still stays high. There's another, so basically that is a very detailed description showing that on different benchmarks, that's like Math 500, AMI 2024, 2025, on policy generally produces much better answers. There's a second approach, which we call balance the uplift strength, called adjusting the clipping threshold or encouraging exploration. So we're getting very technical here. Maybe I wouldn't be spending too much time here. It is from the paper DAPO, which is a specific variant of GRPO. The precise formulation is given here. So intuitively, this RIT theta is basically the likelihood ratio we use in training. Then generally to make GRPO stable, we need to add clipping to this likelihood ratio. It's supposed to be fluctuating around 1. You clip at below 1 minus epsilon low, clip at above 1 plus epsilon high. One important observation made by the paper is that you need to decouple those 2 epsilons, make the epsilon high even higher, bigger than epsilon low. So basic idea is that you would like to encourage the model to increase the probabilities assigned to low probability tokens. So the model is able to explore very well. As you probably can see here, we are talking about lots of hacks in the whole system. So that's the reason why I want to really emphasize that different hacks may not really represent the final state of art, in particular many years later. But I hope the insights conveyed by the hacks actually are useful. Let's say if this is motivated by PPO, indeed PPO also has this clipping approach. Here the core observation is that you actually wanted to decouple these clipping thresholds. So somehow indeed strikes some people as a hack. Does perform quite well. In particular, based on the picture I show here, with clip higher, you see on the purple line, generally for the performance, it gets higher. And in terms of generation entropy, it's also high, doesn't really collapse. Okay. Another aspect people have actually considered in the past in terms of train longer is actually to add a loss to encourage entropy directly. Because we have been talking about this entropy collapse issue. When you train longer, the model only learns to produce one answer. It's not ideal. then naturally you could also add a loss function. You say that what about I try to maintain the entropy at a certain level. And then there are also lots of different tricks in constructing the loss, make sure that the entropy always stays high. For example, you have a certain entropy level, you want to make sure that the loss steers the generation entropy to the particular level of the entropy. There are many things you can do. Still lots of explorations that's necessary, but I hope that the intuition actually is clear. So precisely to encourage entropy directly, following this paper, Skywork or Open Reasoner, what they have done is that they have a particular like entropy loss. So the loss would actually encourage you to increase entropy along training so that entropy doesn't really collapse. And hopefully you also achieve a higher test accuracy as being shown on the picture on the left. Okay, so that's one aspect of train longer. There's also another aspect of train on more difficult prompts and tasks. So in the same entropy mechanism paper, actually along with many different papers in the community, people have been thinking about how to actually capture the aspects of separating the model's performance on hard prompts and on simpler prompts. So they have a quite interesting plot here. So basically, on the left, we'll be talking about what exactly we are plotting in terms of its covariance. So the intuition is that I want to track something which is related to the correlation between the generation likelihoods of the sequence with the sequence quality or the advantage. So basically, I would like to use this covariance between log probability of the whole sequence to the advantage we use in reinforcement learning. We're getting slightly technical here, but without looking at too much details, it's basically trying to figure out whether I'm able to align the confidence of generating certain high quality answers with the final performance. Ideally, what's supposed to happen is that the model is supposed to be very confident in generating the right answers. It's supposed to be quite uncertain in generating the wrong answers. That would be fantastic because next time I prompt the model is more likely to generate the right answer because it's more confident. So on the right, I'm showing a picture basically listing the training curves of subsets of the data sets corresponding to different levels of accuracy. So basically, one can see that for the curves corresponding to very low accuracy, which is purple curve, accuracy 0.125, you see that this correlation stays very low. It really means that the model is not able to very confidently generate the right answers. So for the model, for the questions that's actually very easy, you'll be able to see generally the correlation is higher. So that's actually also an important metric we are trying to track. And on the left, I have another figure, which is also a very interesting observation made by people in the past. It's really about how you actually construct interesting training sets. So what this one has been showing is the following. So I would like to train on multiple different training sets. I'm showing a couple of data sets, Dapple Math, GSM-8K, yours RL data, yours RL difficult. RL difficult is more difficult data set. And on the right, I'm basically checking the validation accuracy on exactly the same validation sets. I'm trying to see by training on different data sets, actually, what is the final validation accuracy, what's the pattern of its evolution. And the paper did observe something very interesting. For example, a GSM-8K actually refers to the curve at the very bottom. So what that precisely shows that, well, when we are able to train this, we found different data points corresponding to different entropy. One trend clearly, when the entropy is higher, the final performance is better, which is a very good trend. But the second thing one wants to see is that if you only train on GSM-8K, it really appears that your final validation accuracy is low. In some sense, it's really because GSM-8K is too easy. You train these too easy data sets, you shouldn't really expect the model to behave very well on some very challenging tasks. But another really interesting observation you can make is that there's a URL data and URL data difficult. Then looking at the curve, actually the URL data difficult also is below the curve of URL data. And URL data contains the difficult data set, also contains something that's actually not that difficult. So somehow it also shows something about the current learning paradigm, which is that you basically blindly throw in super hard prompts. You say that, wow, I really hope you're able to learn. I give you very good feedback. Hopefully you'll be able to solve it. Unfortunately, the LLM itself or the existing algorithms are not smart enough to really capture this. It didn't really learn how to actually do very well. So somehow you need to somehow combine very well different types of data, really make sure it can learn very well. So many different approaches have been proposed in the past. Here I'm talking about one approach proposed in the GRPO lead paper, which is very intuitive, still strikes some people as hacks, but I think the intuition is interesting. Has many intuitions. One intuition was basically saying that, well, maybe in order to provide the signal to the LLMs, suppose it is a very hard prompt and you got it right, I'm supposed to reward you even more because it's supposed to be very hard. It is very simple prompt, you got it right, maybe I shouldn't be rewarding you that much because it's simple. You're supposed to have already captured this. And there are many aspects captured by the paper. For example, there's one answer, you got this question correct, but unfortunately, you produced the answer that's too long. I also would like to penalize you because you're supposed to give a very simple answer. The question isn't that hard. Of course, also if you give something wrong, I also give you really negative answer, really a negative feedback. So many things we can do. So in the paper, it did show that it has many different approaches to actually adjust the corresponding rewards. One can see that if you really adjust the weights for different samples corresponding to an advantage or corresponding to its difficulty, and then performance gets improved. You explicitly penalize the very long generations, many others, then the quality also becomes better. So could really give rise to lots of interesting ideas. Okay, so that's on the hardware prompt side. Very clearly, you can see that this problem is widely open. It's really not clear in the community that people have figured out the right approach, ultimate approach in solving this. There's one last aspect I want to emphasize, which is called sample better. That also appears to be a very important aspect of our algorithm. The whole idea is that you should sample better so we can train on more diverse responses with high quality rewards. Goes back to the original intuition. If you're not able to sample lots of diverse queries, answers with high quality, then you'll be in trouble. So two things I want to talk about. On the left, I talk about so-called parallel reasoning. Ideas could be very simple. There are so many variants of this approach. I'm talking about this paper called GenSelect. Idea is that, so I actually do have this slide here. So basically, when you finally ask LLM to produce answer, you say that what about you do not just directly give me an answer, always give you a very complex prompt on the right, maybe ask you to come up with like 32 different answers, right? 32 different answers, then give the prompt. I say that, so what about you basically select one of the answers from the 32? Then ideally here, as you can see from the answers, generally it's the final accuracy becomes so much better because the LLM really is given more time to figure out the right answer and is able to pick the better one. Another one I want to talk about is another recent paper called the proposing algorithm called DeepConf. So that intuition is also about improving majority voting. So the point is that, say, without this quite sophisticated sampling method, say you want to sample the LLM like 32 times to produce the answer, you just give the same prompt, try 32 times, get answer, conduct final majority voting. But one potential issue is that among the 32 times of sampling, maybe certain trajectories of very low quality. Maybe you should just know at the very beginning or very early on that trajectory is just wrong. If you knew this, you're actually not supposed to include that in the final majority voting. You're supposed to only include those trajectories that's actually likely to become part of the right answer. So the idea of DeepConf is to say that I would like to track the generation confidence of these trajectories. For those trajectories with very low generation confidence, I just believe that model isn't even sure what it's doing. When the model isn't even sure what it's doing, I basically would not include the model or assign a very low weight in the final majority voting so that it should be able to produce a better answer. So on the right, I'm showing some of the results. For example, on the same model, GPT-OSS 120B, if you use the DeepConf compared to the consensus, which is basically majority voting, it actually improves because indeed you're able to discard some of the bad outputs of the model. So that's essentially what I wanted to talk about. Let me summarize the content. Putting everything together in the SFT data, you need to have very good expert demonstrations. RLI recipe, you need to focus on train longer, sample better, train harder. And ideally, what community is supposed to be doing is really to solve everything as a whole. You want to have a collection where we curate environments and verifiers, scale up intelligence. You need to figure out the best definition what intelligence is. You need to be able to release algorithms to train longer, harder prompts with diverse responses. You want to cross sources, community with all the community efforts. You also want to make sure analyze the strengths and weaknesses of benchmarks, including in the collection, everyone can use it, and also release good algorithms for everybody to experiment on. It's going to be my final slide. Hopefully, after today's lecture, we have shared some interesting observations we have made. But my real hope is that we have stimulated your interest in this area. Because one thing I really want to emphasize is that this area is still very immature. Lots of things we really haven't figured out. And the general perspective we have is that we really want to bridge the gap between human learning and system learning. Humans engage in many different environments, focus on some lessons more than others. We can explore ourselves or learn from teachers. We often evaluate the 4-hour intelligence on different tasks. How do we exactly do that for LLMs? In many cases, it's really unclear. So we really would like to encourage the community efforts to join us in this whole effort to collectively produce the strongest agentic intelligence. Thank you.